is on section 4 of chapter 2. It is about continuity. First, let's look at the definitions of continuity at a point. So if a function's f is continuous at c when these three conditions are met. So the three conditions are, first, f of c is defined. So the function is defined at the point c. Second, the limit of the function's f of x when x goes to c exists. Okay. And then last, the limit of the functions when x goes to c is the same as the function value when x equals to c. So if you look at a functions, for an example, this is x, this is y, and this is the graph of the function f of x. And this is a point C where you're going to look at this function to see whether this function is continuous at x equal to c or not. Using this graph, the first conditions is f of c is defined. So it's actually, f of c is defined is when you plug c into the function, you have y values, right? F of c is defined. And the second condition is the limit of the function f of x when x goes to c. So you can try to, so when x goes to c from the left, and this is when x goes to c from the right, yes, they approach into the same point from the left and from the right. Third, the limit of the function f of x when x goes to c does exist. And the last conditions is the limit of this function when x equals to c, x goes to c is the same as the function value when x equals to c. And in these pictures, yes, they are the same. So this function is approaching to the point here, and the point here is actually the value of the function f of x when x is c. All right, let's look at the next three functions here. And this is these three functions. You want to determine which functions are continuous at the point x equal to c. If a function is discontinuous, provide your reasoning. So if I look at this function sine of pi over x, and we have the irrational form here. So that means when x equal to 0, this function's f of x is undefined. So when that I know that f of 0 is undefined, right? You cannot plug 0 into x to find f of 0. Since f of 0 is undefined, then this function's here, f of x, is not continuous at x equals to 0. All right, go to the next functions. And again, in this function, we have a rational form here. And in the denominator, there's two values that would make this denominator equals to 0. These values are 4 and -4. So that means f of -4 is undefined, because if you plug -4 into x, it will give you a 0 in the denominator. That means f of x is not continuous at the point x equals to -4. All right, also this function's f of x here is not continuous when x equals to 4, or x equals to 4. All right, the next functions, you have a piecewise functions when you have different functions on different intervals. So when x less than or equals to 1, the function equals to 2. And if x is greater than 1, the function equals to -2. So this is 2, this is -2, this is x, this is y. And as you can see that when x goes to 1 here, the limit of the functions f of x doesn't exist when x goes to 1. So this is the second conditions, right? The limit doesn't exist. That we can conclude that the function f of x is not continuous at x equals to 1 because the limit doesn't exist. All right, so this is the definitions of continuity at a point. And from the continuity at a point, we can generalize it into the definitions of continuity on an open interval. So a function is E continuous on an open interval AB when the function is continuous at each point in the interval. So it continuous everywhere on the interval A to B. A function that is continuous on the entire real number lines is everywhere continuous, or continuous everywhere. All right, so if we look at this three graph here, graph number 1, 2, and 3. I have 3 different graphs that illustrates, each illustrates 3 different conditions where the functions is not continuous at a point. And then if we want to look at these 3 functions on an open interval, we can put an open interval A and B here. A, B, A, B. So let's look at the first graph. This is the graph of functions when the functions is not continuous when x equals to c. Because if you look at these functions at x goes to c, the functions approach to from the left goes down to negative infinity, and then the functions approach from the right goes up to positive infinity. The limit of the functions, let's say f of x when x goes to c, doesn't exist. That means the functions f of x is not continuous at x equals to c. That means this function f of x is not continuous on the open interval from a to b. It's not continuous on the interval from a to b. All right. So go to the second graph. So the second graph shows us functions where, again, the limit of the functions f of x here, f of c, right, when x equals to c is defined. So you have a value for f of c, but then again, the functions, the limit of these functions when x goes to c doesn't exist. So you can conclude that this function f of x also is not continuous at x equals to c, and also is not continuous when x equals to, also it's not continuous on the open interval from a to b. Well, now look at the third graph. So this graph here will shows you that as you can see this graph here, the limit of the functions when x goes to c does exist, right? However, the limit of the functions x goes to c is not the same as the function's value when x equals to c. So when x equals to c, the function values is 0. But then the limit of this function when x goes to c is a different point here. So again, the functions f of x is not continuous at x equals to c, and also this is not continuous from on the open interval. So these three functions are not continuous at x equals to c, and also they're not continuous on the interval from a to b. Now let's discuss the continuity of each functions in example number 9. So the first functions, you can see right away that the functions here is not defined when x equals to 1. So f of 1 is not defined, and it's defined everywhere else. Thus, f of x is continuous on, let's say, from everywhere except x equals to 1. Or you can say that f of x is continuous on all the real number but 1. Okay. Similarly, the function g of x here is also undefined when x equals to 1, but it's defined everywhere else. So then the conclusions for this is the same as the conclusion for the first example. All right, now go to the next examples. Here, in the third example, the function h of x, you have a piecewise functions. And when you have a piecewise function, you have to be careful where the functions break down. So look at this examples here. This is a function x squared plus 2 when x less than 0. So I sketch the function x squared plus 2 on the left side of 0. And I sketch the function e to the x on the right side of 0 here. All right, and you can see right where there's a gap at x equal to 0. That means the functions is discontinuous, right? The functions f of, this is function h of x. When x goes to 0, the limit of this function when x goes to 0 doesn't exist. That means the function h of x is not continuous. On the real number is not continuous. Is not continuous at x equals to 0. So that means h of x is continuous everywhere, right, on the real numbers, but 0. Or if you want to use the interval notations, you can say h of x is continuous on negative infinity to 0 and union with 0 to infinity. So you have an open interval, so that means it doesn't include 0. If you want to put the interval notations here, you can say that f of x is continuous, right, on negative infinity to 1, union with 1 and positive infinity. All right, let's look at exercise number 4. You are asked to find the constant a and b, or just a constant a in g of x, such that the function is continuous on the entire real line. That means you want to determine a and b, or a here, so that this function f of x and g of x are continuous everywhere from negative infinity to positive infinity. So when I graph this first function f of x here, it's a piecewise functions, right? When x less than negative 3 is y equals to equals to +7. When x is greater than or equals to 4, y equals to -7. And when x is in between -3 and 4, y is a line, right? Ax plus b, it's just the equation of a line. So I connected the 2 dots here to create this line from -3 to 4. So then in order to have these functions to be continuous everywhere, I need to make sure that there's no jumps, right? There's no holes, there's no discontinuity anywhere. And the only 2 places where I need to pay attention to is when x equals to -3 and when x equals to 4. So you can see then x equals -3, I connect the first function to the second functions. When x equals to 4, I connect the second function to the third function. So these 2 points here are the special point where I need to look out for. And I need to make sure that the function is smooth at these 2 points. Smooth means the functions are connected here, okay? So that idea helps me to think that, oh, in order to determine a and b for the second functions here, I need to make sure that this line will passes through this point and this point to connect these 2 lines together. So the problem turns out to be find the line y equals ax plus b such that it passes the point -3, 7, and the point 4 and -7. And we know how to find a line that passes through -3, 7, 4, 7. First, we can find the slope. So the slope equals to, right, 7, -7 over -3, -4, and you will have 14, -7, which is -2. Slope is -2. It makes sense, right? Because this line here is decreasing. All right, now you have a slope, then you can just plug the slope into the line and a point, pick a point and plug into the line. So I pick the first point. So pick the first point, I have 7 equals to -2, -3 plus b. That means b equals to 1. And -2 here is actually a. So I know that, sorry, b equals to a equals to -2 and b equals to 1 is my answer. All right, go to the next piecewise functions. First, I have an exponential functions a times e to the x minus 1 plus 3. And second, I have an arctan function. So this is the graph of arctan. Okay, and then this is the graph of the exponential functions. And since you have arctan x minus 1 plus 2, I think I have to move this up to 2. Move this up a little bit. All right, so when x equals to 1, again, 1 is the point where we want to pay attention to, because it's the point where it's connects the two functions together. And in order for this function g of x to be continuous everywhere, this graph here has to, so the red one, the red graph, has to connect to the blue graph. All right, some point at when x equals to 1. So we need to find a value of a such that this graph here is the same. So these two graphs connect at this point. All right. Now, when x equals to 1, I want to plug a e to the 1 minus 1 plus 3. So when you plug the value 1 into the x here, you can find the values of the graph, the red graph functions, right? And if you want the red graph meet the blue graph at the point x equals to 1, you also plug the point x equals 1 into the second graph. Say arctan 1 minus 1 plus 2. And this is 1 minus 1 is 0. A to the 0 is 1. So on the left side, you have a plus 3. On the right side, arctan of 0 should be 0 and plus 2. So you can solve for a, which is 1, negative 1. So when a equals to negative 1, the graph will look like this. Negative 1, so you flip the red graph over the x-axis. You flip it over the x-axis, and you should meet it here. And then again, the blue graph is tangents of the arctangents here, and then the red graph, the black graph is the new graph when a equals to negative 1, and then you can see that the two graphs meet at the point x equals to 1. Again, the black graph is the reflections of the red graph over the x of y over the x-axis. All right, next we're going to discuss about the one-sided limit.